All right. Welcome back to the Haskell Implementers Workshop. My name is Andres Lö. I'm the session chair for this session. In this session, we're going to have 3 regular talks, and then at the end, there will be the GHC update by Simon Peyton-Jones. And as a bit of advance warning, that will probably run over into the break. So we're probably going to use most of the break time for that as well, because we expect this to be interactive with lots of questions. The first speaker is Richard Eisenberg, and he's going to talk about generalization is hard, but somebody's got to do it. Richard.
Thanks for that introduction. And thanks for having me here at Haskell Implementers Workshop. This is a talk about generalization in GHC. So what do I mean by that? This is really about how do we infer the type of a definition that doesn't have a type signature, right? If I say id x equals x, well, that of course can operate on int or on bool. And so how do we determine that we can do that? And so this talk is all about that because it turned out to be much more subtle than we might think. So the code for the talk is available here. This file that we're looking at, you can download it if you want to sort of follow along. You don't have to, though. We'll be sort of bouncing back and forth within the file during the talk. Let's see. So here is how generalization is done. This is all, by the way, extracted from mostly this decide quantification function within GHC. We're not going to be looking at GHC source code today, though. But in case you want to look, you can go there. And what we're going to do is really talk about these 7 steps, or really steps 3 through 7. So this both is the recipe for how we do inference/generalization, and also the outline for the talk. The idea here is that when we first see a function, something like id x equals x, we're going to generate constraints. And that gives us the first few steps, or rather that gives us the sort of the framework of what the relationship is among the different types. So for example, if I have something like it, or it wouldn't be it, fxy equals x comma y, then GHC will say that, oh, x has type A0, y has type B0. Here, I'm using A0 and B0 to mean unification variables. This is a type variable, but it's a type variable for an as yet determined type. And then we'll pretty quickly see that A0 must equal B0, right? Because in the right-hand side, we have x and y both used in the same list. And so that will produce this equality constraint that A0 must equal B0. The next step of inference is to simplify the constraints. So in this case, when we see A0 equals B0, well, that's a very easy constraint to solve. We'll just choose A0 equals B0. And then now we just have one type for both of them. It will turn out that there's no further work that we can do here. There's no other constraints on these types. And so we'll just say that this function takes 2 variables of type B and will return a list containing element of type B. So that's generate constraints and simplify constraints. Constraints also include class constraints. We might have ordered constraints and constraints, things like that in here. We're actually not going to focus too much on these steps. I wanted to give a little background on what's going on here. Most of what we're going to talk about is what happens afterward. So let me get rid of this stuff here and really focus on this stuff down here. So once we've generated and simplified these constraints, then how do we actually go from that to determining the type? Henley-Milner would have you believe that we just look for all type variables that aren't in an outer scope. And then we generalize over those. And that's kind of true, but of course, GHC makes things trickier. So we're going to go through a bunch of examples that illustrate all of these other steps here. So let's jump down into the code. So this is real code that's running in GHCI here. I have a very recent build of head. So I guess you could call this either 9.2 or maybe even 9.4. And we're going to start with a fairly simple definition here. X equals 5. We can see, well, what's the type of x? It's integer. And already something interesting is going on here. That's because what we're going to see on the right-hand side is 5. It doesn't have type int. It has type A0. And we also get a constraint num A0. So we can quickly determine if 5 has type A0, then X also has type A0. But now, do I want to generalize over A0 or do I not want to generalize over A0? There's not further constraint. So I could say that X has type num A, arrow A. And indeed, that works. But that's not what happens. And that's because of something called the monomorphism restriction. The monomorphism restriction says that when we have a definition that does not look like a function, and X doesn't look like a function because there's nothing here, there's no argument to the left of the equal sign. When we have one of those, we will not infer any constraints. That's the monomorphism restriction. There's some other subtleties to it around mutual recursion and whatnot, but that's the simpler form. If we look at our recipe here, so the first step, the step 3, this first step of generalization is to determine ungeneralizable variables. GHC calls these the mono-TVs. So 3b has variables mentioned in a constraint when the monomorphism restriction applies. So down in our example here, A0 is mentioned in this num constraint, and so A0 becomes an ungeneralizable variable. We won't generalize it, and then the reason that we get the type X of type integer down here is because GHC does defaulting and says, well, I know that there should be some type A0, I don't know what, but it's definitely going to be a number. And so what's a good number out there? Well, there's sort of a list of different number types that GHC will try in order. And the first one is integer. That works. And then X is assigned type integer here. Okay, let's move on to the next example. So the next example is Warble. This also compiles. But actually, the interesting thing is not the type of Warble that I want to look at, but the type of verb. So in order to understand what's going on here, we're going to have to convince GHC to tell us what the type of verb is. And to do that, we can dedump TC, which that will output the result of the type checker. And so in here, we get stuff about Warble, but we still don't see the type of this local definition verb. So I need even more here. I need fprint type checker elaboration. Now, when I load, whoops, what's gone on? Something strange has happened. Okay, let's try that again. There we go. Now we get the type checker elaboration, which sort of buried in a lot of other gunk will actually tell us the type of verb. Okay, so now having sort of set up that we can see it, let's analyze what's going on here. So if we just look at this verb y definition, well, we'll see, well, this mentions X. So X is going to have type A0 for some unknown type A0. Y is going to have some type B0. We quickly learn, because we're adding them together, and plus takes two things of the same type. So we quickly learn that A0 has to equal B0. And we need this to be, we have a num constraint A0. But the question is can we generalize all of this? Could we say then that verb will have type, say, num b to b to b, right? It takes one argument, it returns one result, it has to be a number. Is that an okay type for verb? No, it's not. And that's because verb here on the right-hand side mentions X, which is a fixed type from out here. And so because of this, this type variable B0 or A0, sort of however A0 and B0 get resolved together, that is an ungeneralizable type variable. This is the very much more classic sort of Hindley-Milner, we can't generalize a variable that's already in scope. And so that's why down here, verb gets this type, P arrow P, not a for all type like Warble gets. So verb just gets this local type, or this type rather, that just mentions this already in scope P. Okay, so that's the Warble example. And again, going back to our outline, that's demonstrating how we won't generalize variables from an outer scope. The last part here for ungeneralizable variables is variables related by equality constraints to the above. So to do this, we're going to need a slightly more involved example. Let me comment this out, actually. So here, I have a type family TF and a function inject, which just takes something of type A and changes it to have type TFA. we'll end up needing type families to sort of make GHC a little not so clever, so that we can witness some of the strange things that happen. Now, my function here, f, I actually give it a type signature. I don't care about f, I care about g. And if I try to compile this, we're going to get a type error. About A0 is ambiguous. So let's try to understand what's going on here. So X is brought into scope. X has type A, as we can see from the type signature for F. Then, when we look at the definition of Y, well, we don't know what type Y is going to have. So I'm just going to call it A0. I would normally call it B0 just to keep it different from A, but A0 is what the error message uses. So we're going to guess that Y has type A0. Then, from the right-hand side, we see that inject X and inject Y are used in the same list. So if these are used in the same list, then that must mean that FA equals FA0. Now we have to determine, will we generalize? Can we generalize A0? And according to our rules, back up here, no, we can't. That's because A is a variable from an outer scope, and A0 is related to A by an equality constraint. Whoops, this equality constraint right here. And so GHC won't generalize. Instead, it will infer a type something like this, A0 to list of FVA. But then it can't figure out ever what A0 should be. Because there's no call sites of G. There's nothing for us to sort of use to figure out this next step. And so we get this error that A0 is ambiguous. This would not be solved just by enabling allow ambiguous types, right? It's not that we have an ambiguous type signature for a function. It's that really A0 is ambiguous. We just don't know what it should be. What's interesting here is that there is a perfectly good type for G, this one. And if I try to compile, this gets accepted. And so what I've done here is I have indeed generalized A0. I've called it B here. And then I just say that TF of B equals TF of A, where this A is brought into scope up here using scope type variables. So this is a little bit suspect, this variables related by equality constraints, because it actually stops us from inferring the better type for G. Okay, let's move on to the next example. And that's this IDI here. So let's look at the rule. The rule is number 4. After we figure out what the ungeneralizable variables are, then maybe there's still some variables, some of these unification variables we haven't quite sorted out, and we're going to default them. So in the case of IDI, this is a very simple definition. And if we compile this, we can ask, what is the type of IDI? Let's turn on print explicit for alls. And we can see that this is for all P, P arrow P. But what's the kind of P? Well, what GHC won't tell you, because it's just sort of omitted because they're so common, is that P actually has kind type here. But there are other good kinds for P. So I could write instead and that still works. So here now I've said that P is not a lifted type, but actually an unlifted type. So this would be a strict IDI that works only over types of an unlifted kind, or that are represented by an unlifted pointer, I guess. And yet she didn't infer this type. It specifically chose to use lifted types. That's because those are the most common. But this is this example of defaulting. And what's interesting here is that the defaulting mechanism is actually totally different than the defaulting mechanism that we saw earlier for integer, which happens all the way at the very end of type checking. This one, where we default, in this case, a representation variable, that happens during generalization. The next example is this cat-id. So this is using categories id. So we can ask, what is c.id? So it's a method in the category class that works over any A of kind K. Or works over an A of any kind K, I really should have said. So what's the type of cat-id? Oh, not in scope. I guess I have to recompile. Oh, what's going on here? I wasn't expecting this. We need to disable the monomorphism restriction for this one. And now we compile all as well. And we ask, what is the kind of catid? Well, it's what we would expect. It's quantified over K and over the category of kind K and over A of kind K. That's all well and good. If we turn off polykinds, which is on by default in newer GHCs, and I compile everything as well, but now the type of catid, it defaults all of these kinds to just plain old type. And this is all part of this defaulting step. Okay, after we've determined the monovariables and then defaulted, we now have to choose the actual quantified variables. So we have a few more examples to demonstrate that. That's down here. And let me re-enable the monomorphism restriction, although I don't think it comes into play right away. So if we look down here, well, what's going to be, what's going on here? So we have show 5. 5 has type A0 for num A0, but printed has type string. And we're also going to have show A0, aren't we? And so now we have to figure out, are we going to generalize this A0? We don't really know what it is. No, we're not, and that's because A0 isn't mentioned anywhere in the type string. And so because of that, we don't know really what to do with A0, and so we're going to use our defaulting scheme. And we can see that here in this output that show is actually specialized to integer. So here the default matters, right? If I default to double, I'm going to get a different string. Length has a similar issue, except here there's really no class constraints. And so the defaulting works differently. It defaults to sort of an internal type any. That's because GHC determines that no matter what we choose as the element type of this list, we're going to get the same result. Let's see, going back to our little outline here. So that's this 5a. We're only going to quantify over variables that are mentioned in the body after the fat arrow sign of the inferred type, as well as variables related to those in a constraint. So that's our next example with frob and zerp here. So with frob and zerp, here I have frozu x, which calls frobsrip x5. So frobsrip is this function here. And frobsrip will give rise to a constraint frobsrip of a, b. So here we're going to have x of type A0, 5 has type B0. We're going to get a num B0 constraint, but then we're also going to get a frobsrip A0, B0. The type of frozu we're going to see is, what is it going to be? A0 to unit. So normally we could generalize over A0, but not over B0 because B0 isn't mentioned in this type of frozu. But because it's related to A0 in this frobsrip constraint, we will generalize over B0. And indeed, we can see that if we look at the type of frozu. Oh, not in scope. Maybe I have to recompile again. Here we get frobsrip a, b, num b, these constraints, even though b isn't mentioned over here. So this is an ambiguous type, but it's still the type that GHC will infer. By contrast, we can look at fro_zu, which separates out the frob and the zerp. And so now we're going to get a separate frob a and zerp b constraint. And then now we get errors because it's not going to generalize over that b. Instead, it complains about ambiguous types. It calls it A0 here, but really the problem is that we can't satisfy zerp of A0. The last step here is, let's just comment out this whole region. I'm going to leave some time for questions. So the last example that we're going to look at is let's see, it's choose the quantified, or sorry, is remove redundant superclasses. This choose the quantified constraints is really about, we want to also figure out what goes to the left of the fat arrow. And it's only going to be the constraints that mention the quantified variables. That one's actually fairly simple. This last step is about removing redundant superclasses. So here, check ruffle, right? on the right-hand side, this gives rise to both an eq A0. If we have X as type A0, this will give rise to eq A0 and ORed A0. And we could imagine quantifying over both, but that would be a little silly. It's much better to get this type here that just mentions ORed A by removing the redundant eq A superclass. So there's actually a lot more than we've seen in generalization. Partial type signatures makes this much more difficult. There could be mutual recursion, implicit parameters, functional dependency, something called naughty quantification. You can search the GHC source code for more about that, as well as all the usual implementation details. But I'm hoping this overview gives you some ideas of what will happen in GHC when you have a definition without a type signature. Thanks very much.
Okay, thank you, Richard, for the great overview. I'm checking questions. So there is a question by Adam Gundry. I'm just going to read it because we don't have very much time. What's the motivation for Rule 3C? You showed an example where it was unhelpful, but when is it helpful?
So I actually think that Rule 3C is unhelpful. So there's a patch that I'm working on that gets rid of derived constraints in GHC that actually changes Rule 3C to be variables that are sort of implicated by a functional dependency from those that are fixed, right? If we have fixed variables on the outside that control variables that haven't otherwise been fixed through a functional dependency, we're going to fix those, but not this just related by inequality constraint for exactly the problem shown in this talk.
Okay. Then there is a question by Matthias. When we are not running in interactive mode, we get a lot more ambiguous type variable errors for some of these, right? I guess it's a leading question.
I don't think that there should be a difference between interactive mode and not interactive mode. I guess the only real difference I can think of is that interactive mode uses something called extended default rules, which makes it more aggressive in defaulting. But I don't think any of the examples, at least in this talk, trigger those rules. So maybe we can talk offline about the example you're thinking of.
Yeah. Okay. Then we have a question by Joachim. How principled is this algorithm? Is it based on what works best in practice while still being feasible, or is there a more fundamental guiding principle here, principal types or something like that?
That's a good question. You know, this has sort of grown over time. I don't know that there's a sort of a concrete analysis of it. That's a great question, and I don't really have a good answer. I'd be happy to discuss that. Certainly, we need to not generalize over variables from an outer scope. That's all about principal types. And then the rest is just sort of funny features in GHC, right? Monomorphism restriction, defaulting has to do with these extra fancy features. Avoiding ambiguous types. I don't know. I don't have a great answer.
Yeah, so there are some comments by Simon, which I'll just read as well. It's worth stressing that there is something a bit arbitrary about the generalization rules. A safe and principled thing to do is to abstract over all unsolved constraints, but you get huge types that way. And yeah, I think
yes.
Let's and then there's one final related question by Roger Bosman. Can you elaborate on the decision to default instead of generalize? Do you prefer simpler, slightly less general types over potentially confusing the user?
Well, there's sort of two different places we saw defaulting. One was around the monomorphism restriction, which has to do with sort of, do we want unexpected, runtime consequences of having a constrained type? The other defaulting has to do with restrictions in compiling levity polymorphism, right? We can't generalize over representations, so that's no good. The kind variables, the fact that we default them, I think that's a bug because I would like to remove no polykines at this point. Defaulting multiplicity variables is about simpler types. So there's actually sort of different priorities here, but there is generally a desire to infer simpler types because these complicated types are confusing. And so how do we balance out generality with simplicity? I don't know.
Okay, thank you again, Richard. We have to
Thanks.
stop here, unfortunately, because we're short on time.